So I'd like to introduce Dr. Sanfeng Wu, who's going to talk about a route to quantum knots with anyons.
Yeah.
So
Thanks, Peter. I'm the right one. Yeah. I don't have audio, so I don't need this. Only, yeah, this side. Hello. Okay. Good afternoon. Again, I'm Sanfeng Wu. I'm a condensed matter experimentalist. My title today is A Road to Quantum Knots. So to explain why I'm interested in knots and quantum knots, so I think I have to talk a little bit about history and actually the time before history. So this book, I Ching, one of the oldest books in human history, is formed about 3,000 years ago. So it's also the root of Chinese philosophy and culture. In this book, there's a following text, which I translate into English, of course. It says, in the remote past of this book, so it's a few thousand years ago, the society was organized by knotted ropes. Later, it was changed to a scratch writing system by sages. And this is why when we learn history, learn Chinese history in middle school, the history textbook started with these sages, such as Fuxi, who lived about 5,000 years ago. And he laid the foundation of Chinese scratch writing systems, the Chinese characters. And after these sages, we have history. We have the written history. And our history is written by making scratches on the surface of oracle bones, or making scratch on the surface of bamboos. And later, we use brush to scratch surface of papers. And nowadays, we make tiny little scratches, up and downs and 0 1s, on the surface of electricity, on the electricity or magnetism profiles on the surface of a wafer. So this is the history we have. According to this quote, before this history, we actually have a long time, maybe 1,000 years period, that our culture or society is organized by the knotted ropes. This is not unique to Chinese history. It's also found in such as old Hawaii and also South America. Especially in South America, the Inca culture actually used the knotted ropes until only about 300 years ago. It's very recent. And also, I just heard MIT has a research institute to study how to translate these knotted ropes into real understandable languages. So as a condensed matter physicist, my view of this is actually how to store information in a robust way. Think about the time before history. We do not have the technology that developed. We only rely on the material that exists in nature that just we can work around. The two ways to record information. One is use topology, such as the knotted ropes, essentially the number of holes that you made in your knots. Also, the other way is to find the material, such as oracle bones, then you can make scratches using the geometry, the shapes that you made on the surface of the material. So those two, essentially, two methods to robustly record the information. If you do not have oracle bones, if you live in another, right, in a place you have oracle bones, then topology is a natural way to do such things. So because topology guaranteed naturally the robustness. For example, if you have a simple knot, just a loop made by a string, as long as you do not cut the string, you do anything to the string, you can change A to B, but the topology doesn't change. You can never change A to C where you have different numbers of holes. So topology guarantees the robustness. However, once you have a new material like oracle bones, you can also make a robust information. Now, miniaturization become important. So history tells us this oracle bones wins because you can miniaturize. Our developable history is actually to change the material so you can write in more information in a condensed way to piece of papers and nowadays in silicon wafers. Actually, this is very highlighted by the Moore's law during the past few decades. It tells us the transistors, the tiny scratch that we made on the surface of a wafer, the size decreased exponentially with time until recently we actually reached the limit where we want to actually try to make scratch on very tiny scales on the scale of atoms. So if you want to make scratch to atoms, this is quantum mechanics tell us, you have to ask quantum, because the physics here is driven by quantum mechanics. And we know that quantum state is so fragile that until now we do not know how to make a robust way to keep the quantum information. This means that nowadays we face the same challenge in the quantum world. We want to keep the information robust. As the time before history, like our ancient human beings, they want to keep the information robust. But that's in classical world, here in quantum world. So I like to say in the quantum world, now we are actually at the time before history. So there's many people try to find a oracle bones in the quantum world so that we can continue our skills to make scratches. There's also another group of people try to tie knots, a quantum knots, and I belong to the latter. So what's quantum knot and how you can tie a quantum knot, right? So here is the illustrated in how you tie a classical knot. So this is the way you tie a barrel knot, which is very useful for fishing. So the way you tie this, you actually just simply hold one end of a string, and then you make a braiding operations around itself or around another string. And then you can, these simple actions that can naturally give rise to knot structures. So just simply by braiding, by holding, moving the ends of the ropes. So how we can apply this idea to quantum mechanics particles? It's actually pretty simple. If we have a different way to view some basic situations in quantum mechanics. Let's consider quantum particles that live in 2 dimensions, which means the particle can only move in x and y direction, but not z directions. If you have such particles, let's think about exchange of this position of these 2 particles. Actually, let's think about exchanging them twice, which means essentially equal to you hold one particle and make a loop around the other ones. If you look at this situation in the space-time traces, which means the 2-dimensional x-y space plus the time. And the trace looks very much like the braiding operations that you see here. And this is the fundamental elements to tie a knot, right? Now, if you have multiple quantum particles in 2 dimensions, you can make a very complex exchange the position and the braiding so that you can make a complex quantum knots. So this idea seems beautiful. But if you look at the problems, if you look at the textbook of quantum mechanics, it will tell you the fundamental quantum particles are either bosons or fermions. That means after the exchange of 2 particles, the quantum state of these particles only acquire a sign or not. It just keep the same. So even though you have very complicated structures, the final state has nothing different with the initial state except a sign. So the quantum state essentially keep the same. However, we can go beyond this fundamental boson fermion classification in condensed matter physics. So in condensed matter physics, actually there exists some exotic particles called anyons. So these anyons, actually after you exchange them, the phase can be neither 1 or -1. It can be arbitrary phase. And this is called anyons. However, the anyons does not help either, because it's also a phase. So after you exchange the particles, final state only change the phase, just not a 1 or -1, but maybe pi/3, things like this. So it doesn't help too, because the state is still the same. So theorists are very smart. They come up a very exotic idea. They say there might be some non-abelian anyons, which means after you exchange them, the state can be totally different. So they can be completely distinct from the original state, which means and in this case, the quantum knot in the space-time now determine the final state after you do the braiding operations. And this is very exotic. In this case, the quantum knot structure in space-time become meaningful, and you can use them to code information. So it's a powerful method. Of course, it's robust because it's a knot. It's similar to the knot the ropes but it's in quantum mechanics way. So problems, there's no evidence, no solid evidence for any existing material, particles, quasi-particles that belongs to the non-abelian anyons yet. We do not have solid evidence for that. So how to find the non-abelian anyon became a real problem in order to make an idea become true. So it's until 2001, Kitaev, a professor in Caltech, he proposed a toy model. It's a very simple model and tried to figure out how we can realize this. It's probably the most complicated slides I have today, but it's a beautiful idea. I will try to give a brief overview of what's going on here. So he's thinking about a very simple lattice of atoms, and each atom actually can be viewed as the sites for electrons to occupy. In quantum mechanics, occupation for electrons is described by complex operators. So complex operators actually has two components, the real part and the imaginary part. So he's smartly view each side as two subsites, demonstrated by the little blue sides. And now the lattice actually can be viewed by this little blue sides, where two of them are paired together to form the original atom sites. Now he introduced exotic interactions between the sites, such that the little blue balls now repair themselves in following way, denoted by the green link here, such that there will be two unpaired subsites at the end of the lattice. This means that if you only look at the subsite at the end of the sites, you have a half electron site occupied here, because the little ball is essentially a half of electron site. So you have, then we can create such half electron state, which I call it Mariana states. This is maybe more complicated, but I have a simple illustrations. It means that Kitaev proposed a toy model that can, in condensed matter systems, that you can chop a single electrons into two halves, and each half are anyons. And actually, they found it's one kind of non-abelian anyons. It's a material, it's a quasi-particle that we want for tying the knot. However, Kitaev do not know how to realize this idea in real materials. And that's a real problem for experimentalists, right? It's until 2008, Liang Fu, now MIT professors, and Charles Kim proposed a proposal that can realize such idea. They start with some material, also exotic material, called the quantum spin Hall topological insulators. It's exotic, it's rare, but it exists. It's not like the Kitaev chain, which we do not know where to find them. So there's some rare materials called this. Well, despite the name, actually it's only the unique property here we need is only it's an insulator, and it's topological insulator means the interior is the insulator. It do not conduct electrons. However, at the edge, at the boundary of this insulator, which is two-dimensional insulator, there's a conducting mode where spin up electrons and spin down electrons transport in the opposite directions. If you have such strange materials, and then what they propose that if you coat those materials with a superconductor, very Euro superconductors at the two sides in this case, and then you hope that the superconductivity can be induced into the edge of this quantum spin Hall insulators. And once you do that, once you can achieve the proximity-induced superconductivity to this edge, then they demonstrate such edge is equivalent or essentially equivalent to the Kitaev chain. So that we know we can start from known materials, existing materials, to construct such a toy model. Well, to summarize what I have just talked is actually how we experimentalists to tie the knot. So if you, for example, the coaxial knot, if you want to tie a knot, it's better to find a rope. And if you want to make a rope, it's better to find a cotton. Then you can make a rope and tie a knot. What I'm talking about in the quantum world, in the similar analog, is that if you want to tie a quantum knot, then it's better to find a quantum rope, which is essentially the Kitaev chain that I mentioned. And if you want to have a Kitaev chain, you need some materials like quantum cottons. So it's actually superconductor and topological insulators. You combine two different materials, then you can make a quantum rope. This is a beautiful ideas. Of course, now we can, as experimentalists, we can do experiments. And this is the case, of course, starting from 2012. The first demonstration tried to realize these ideas. They have then followed this experiment as many other experimental systems, despite they have different materials, but they're essentially the same, a combination of two kinds of materials. One is the superconductor, the other one is topological insulator, or some material that behave like the topological insulator behaviors. One mark here I would like to say, they all have same property, which is combination of two different materials. This also presents challenges, because you now want to high quality of materials for both types, and also need high quality materials at the interface in order to realize the model. And that's the common thing for all the existing systems. Also, I have two comments here for these slides. One is, you can see here, there are globally research group from all over the world. but there's no MIT here. MIT series has made a great contribution to these ideas, including Professor Xiaogang Wen, Liang Fu, and Patrick Lee. Experimentalists, we have to hurry up. The other thing is, despite this existing systems, the farthest point they have gone is they try to provide evidence that they do have quantum ropes, but there's no quantum knot has been tied yet. So we still have opportunities. So starting from day one as Pappalardo fellow, I try to identify a new material, new systems to do such a thing, to tie a quantum knot. Okay, so how I can start with? So of course, ask MIT series. So this is a paper published by 4 MIT series, including Yang Fu. They identify a new material, so two-dimensional transition metal dicharacterized, for example, tungsten ditelluride, which is the layered material. Here I show the crystal structures. In each layer, you have 3 layers of atoms, and in the middle is tungsten atoms. Top and bottom, there's telluride atoms. So they predict if you can just get a single layer of this material, these crystals, then the single layer crystals behave just like the topological incident that we mentioned before. So it's an essential component for the idea. So if we can achieve the smaller layer, then you will have insulating bulk and conducting edge where spin up and spin down travel in different directions. So I want to see what's going on in this experiment, whether this prediction is true or not. And this is the optical image of a single layer that we fabricate in lab. Even though it's only a single 3-atom stick, we can still see clearly on the optical images. So now we want to demonstrate whether it's topological insulator or not. To do that, actually, there's some standard check, or relatively standard checks, in order to say whether it's indeed or not the topological insulator. But the answer, I would like to say the answer first, is yes. We do have a very positive, kind of strong evidence to say, yes, it's a quantum spin-Hall insulator. And the key experiment that I want to share with you here today is this simple measurements, which we try to measure the resistance of this monolayer flake as functions of the length of the material. So think about Ohm's law. If you have a resistance, and if you increase the length of resistance, you actually increase the resistance, right? But this is not the case when you fabricate a monolayer tungsten ditelluride to a short limit. If you go the length of the material to about a few hundred nanometers, then you can see, beyond that, with longer length, you do see a kind of Ohm's law behavior. We have longer material, you have a higher resistance. But once you go to a short edge limit, which is below 100 nanometers, this behavior deviates from the Ohm's law significantly. And the resistance do not decrease anymore. It saturates to a number that's only determined by fundamental constant. H is Planck constant, and E is the electron charge. This means this is one of the key hallmark signature of quantum spin-Hall insulator. And we also do some few other checks. The reason to have this quantized conductance is that now the interior of the material do not conduct, so current cannot flow. Now, if you put current into the material, only the edge will flow. However, the edge with spin-up electrons will only flow at the upper edge, and spin-down electron will only flow at the bottom edge, which means you essentially only have 2 quantum channels, which will give you h over E squared per edge, the conductance. And this is the hallmark signature for quantum spin-Hall, and we also checked a few other necessary conditions, and we've realized it's indeed a predict effects for the quantum spin-Hall system for these materials. And another interesting feature I want to mention here is that if we check how robust this quantum spin-Hall state is under the temperature variation, we increase temperature up to 100 kelvins. The state still keep robust up to 100 kelvins, monitored by the conductance. The quantum conductance still keep at 2e squared over h. So this means compared to previous quantum spin-Hall insulators, where this state can only survive to few kelvins, we increase the temperature up to 100 order of magnitude. So this is the first demonstration of high temperature quantum spin-Hall effects, actually. So this means the theories are good. We indeed can tell they can tell the truth, and we checked experimentally, so they predict something real. And if I already talked a lot about the good thing about theories. So if it sounds like the experimentalist is useless, right? But next slides I will show you is not the case. because we discovered another things in this material which has not been predicted by any theorists. It's the superconductivity in these materials. So the device we made is now like this. So it's the same monolayer tungsten ditelluride, and we can measure the resistance. So if we fabricate a metal on top of that, separated by a dielectric insulating layer, so in this device, it's actually realized a monolayer tungsten ditelluride transistor. A transistor means if we apply a voltage to a gate, then we can tune the density of electrons to add electrons into the monolayer, so you can tune an insulator into a metal. So this is the data we have, the conductance as function of the gate voltage you apply here. So this here is the insulating state, but it's insulating still have some finite conductance. That's because the edge is conducting. So it's a topological insulator. And then if we change the gate voltage to a high value, you add electrons to the system, and the system becomes metallic, which means now you actually realize a transistor tuned from off-state insulator to a metallic state. What's interesting here, if I focus on the metallic state, park the gate voltage here, and monitor the resistance of the flake as function of temperature, I see this. So the resistance keeps constant when I decrease the temperature, and suddenly they drop to a very low value at around 1 Kelvin. So this is a behavior looks like superconductivity. Now experimentalists, you can also have a standard check to say whether this is a superconducting transition or not. And the answer is also yes. We did a series of checks, but I'm not going to show the details, but only to tell you that this is indeed a superconducting transitions. Despite that, this number here is not going to 0 yet. That's because a known imperfection in our current device, and we're currently working on new device to remove the imperfection to see the real zeros. But as a summary here, I want to say we discovered the superconductivity in monolayer tungsten ditelluride, and it's very gate tunable because, as I said before, it's tuned from insulator to a superconductor. Like in normal transistor, you tune from insulator to metallic state. Here, we tune from insulator to superconductivity. So this is a very, I think it's a very remarkable discovery, and it provides a lot of new opportunity for superconducting devices. But I'm not going to talk in this direction. I want to draw your attention back to the quantum knots. So we realized two essential components: the quantum spin Hall insulator, topological insulator, and the superconductivity in one materials. Now I summarize what my title means here: a road to quantum knots. So a road to quantum knots means here if I already identify a new material which can be treated as a quantum quantum. And in the future, I can just use gates to design a novel devices so that I can induce the superconductivity in the same material into the edge, which will realize the Kitaev chain as a quantum rope. And then with the quantum rope, I can try to build a quantum knots. So that's the road I mean in the title. And our current status is here. We indeed demonstrate it can has both properties required for quantum knots, and in the future, maybe in the Pappalardo fellowship, we can demonstrate the property of quantum ropes, and to demonstrate we can create quantum knots that requires longer and much more efforts. So now I want to go back to the history, the future of history actually. So we know we have a scratching age and a knotting age in the past. So now I would like to think about Moore's law again. So people often talk about Moore's law in the context of computer history. Now I invite you to think about Moore's law in the human history. Will the end of Moore's law actually the end of the scratching age of human history? Are we standing at the transition point where we're going to go from a scratching age to a new knotting age? Well, this is pure kind of imagination now. Let's tie a quantum knot first. So last slide. So I'd like to acknowledge my collaborators. So the experiment is done in Pablo Harrero's group with graduate student Vala. And in addition to thank those who support my research, I also like to thank those who support my life. It's really Jane, Neil, Pappalardo, the family, who really provide me the opportunity to speak here, and also my own family. Thanks my wife. So if I'm not sure whether our human history will go into another new age, I'm pretty sure my own life has transitioned into a new age. 49 days ago, so this is our baby who is looking into the future in front of MIT Dome. Thank you for your attention.
Thank you. That was just excellent. And this area is really just accelerating incredibly. Our tradition is that Neil and Howard, who actually study for this symposium, get to ask the first question, if they wish.
Well, I'll actually will answer it, although I must apologize that condensed matter has always been troublesome for Howard and I. We're good on many different fields. The question I have, the Majorana particle was discovered in the 30s. Not, I shouldn't say discovered. It was, he postulated the existence.
Yes.
And you use that as your initial example. Have there ever been anybody who's ever been able to create such a particle to date?
Yes, so in the experimental system I just mentioned, there are many systems. They provide evidence to say that, yes. Well, here's a two different story. So the particle that you mentioned, the Majorana predicts the particles in 30.
Where the magnetic field apparently is closed and the electric field, and there's such a way that that doesn't normally exist that I'm aware of.
Yeah, it doesn't normally exist. That's why we need to engineer. And there's two types. So one is in, for example, in the fundamental particle physics. The other one is emergent condensed matter physics, right? So we here focus on the condensed matter physics. Actually, in both systems, I think people are looking for the evidence for that. And there's no solid evidence for both systems. But here in condensed matter, they say they have evidence, but there's also some unambiguities. So that's why we need new systems to really say solid evidence, say it is there. So I would say whether it exists, 0.5, yes or no in between.
It's been about 80 years since they were first
Yes,
postulated.
yes.
Thank you.
Questions from the audience? Mark.
So what determines the energy scale at which these Majorana quasi-particles are supposed to be stable? Because that's important in terms of whether these knots are stable, right?
Yes, yes. So for example, in this system, you have superconducting, right? That's one energy scale. And you induce superconductivity to the edge state. The edge originally have the energy scales, but once you induce the superconductivity to here, actually, because it's not a real superconductor, you induce that, so it's a smaller gap again. So it depends on how, I believe it depends on how large the gap original is and how you induce gap in here, and then that gives you energy scales. And people in the system that already proposed is the energy scale on the order of micron electron volts. But I'm not sure, for example, the system I'm going to study, whether it's large or not. I hope it's large, right? But I'm not sure. Yeah.
Wadi.
Do you have an estimate in an optimistic scenario of like how many orders of magnitude you can improve energy density, information density in the new knotting age as opposed to the scratching age?
Yeah, that's a very good question. Because so in traditional knots, well, that's not much, because as the ropes. Now it's a quantum knot. So it's determined by how many particles you have and how complex the knot structure you have. So here is actually a way it's a quantum mechanical property, right? It's superpositions. So if you can really tune by the exchange interaction and to scan the whole Hilbert space of these quantum particles, then it's a 2 to the n, it's exponentially. So I think it's more like a quantum information scale. So I think that's the answer. So it's determined by number of particles you have, more and you have more. Yeah, exponentially increase.
We have time for one more question. Okay, let's take Shengfei again.